Good day. For today, we are going to learn about differential equation, which is the exact equation and linear equation of order 1. So for the contents of this presentation, we have here our lesson 1, exact equation, its examples, and some assessments for us to answer. Next would be the lesson 2, which is the linear equation of order 1, its examples, and some assessments that we are going to answer. So for our learning objectives in lesson 1, we have here at the end of the lesson, the learners are expected to discuss the concept of exact equations, perform the step-by-step process of solving exact equations, and solve problems involving exact equations.
Hi everyone, let's now start discussing the lesson 1, which is the exact equation, about when can we use exact equation and how to solve differential equation using the exact equation. It was noticed that when an equation can be put in a form of a of x dx plus b of y dy is equals to 0 can be integrated easily. However, some differential equations can be driven in the form of this one, m of xy dx plus n of xy dy is equals to 0, wherein the two terms composes or in the form of x and y, or has a multiple variable or a multi-variable. So to know that we can use the exact equations, first we just simply derive m in terms of y and n in terms of x. And this is now the general solution for our exact equation. Df, wherein our f is in the form of x and y, is equals to m dx plus n dy. Then certainly f of xy is equals to z, c, or a constant, is the general solution of our equation number 1, which is this one. From equation 3, it follows that df is equals to 0, or in the view of equation 2, which is m dx plus n dy, must be also equals to 0. If the equation 1, m dx plus n dy is equals to 0, is an exact equation, then by definition of a function exists such that df is equals to m dx plus n dy. However, in calculus, the df is equals to partial derivation of a function in terms of x dx plus partial derivation of a function in terms of y dy. So, m is equals to the partial derivation of a function in terms of x, and n is equals to partial derivation of a function in terms of y. These two equations leads to the partial derivation of m in terms of y is equals to the second partial derivation of a function in terms of y and x, and the partial derivation of n in terms of x is equals to the second partial derivation of a function in terms of xy. It means that we just simply derive m term in terms of y and n term in terms of x. Again, from calculus, the second partial derivation of a function in terms of y and x must be equal to the second partial derivation of a function in terms of x, y, so that we can use the exact equation, provided these partial derivatives are continuous. Therefore, if equation 1 is an exact equation, then equation 4, which is the partial derivation of m in terms of y, must be equal to the partial derivation of n in terms of x, so that the equation 4 can be satisfied. So to show that if condition 4 is satisfied, then the equation 1 is an exact equation. Let phi of x, y be a function for which the partial derivation of phi in terms of x must be equal to m. The function phi is the result of integrating m dx with respect to x, which holding y constant. Now, the second partial derivation of phi in terms of yx is equals to the partial derivation of m in terms of y. Hence, if the equation 4 is satisfied, then the partial derivation of n in terms of x must be also equal to the second partial derivation of phi in terms of xy. Let us now integrate both sides of this last equation with respect to x, holding y fixed or y constant. In the integration with respect to the x, the arbitrary constant may be any function of y. Let us call it t prime of y, for ease in indicating its integral. The integration of the fifth equation with respect to x yields that the partial derivation of phi with respect to y is equals to the n plus t prime of y. Now, a function f can be exhibited namely, function is equals to the phi of xy minus t of y, for which df is equals to the partial derivation of phi in terms of x dx plus partial derivation of phi also in terms of y dy minus t prime t prime of y dy, which is also equals to m dx plus the equivalent of our partial derivation of phi in terms of y, which is n plus t prime of y dy minus t prime of y dy, is equals to m dx plus n dy, which is a complete proving on our theorem in the next page, which is the theorem 52. If n partial derivation of m in terms of y and partial derivation of n in terms of x are continuous functions of x and y, then a necessary and sufficient condition that the equation 1 m dx plus n dy is equals to 0. B, an exact equation is that partial derivation of m in terms of y must be equal to the partial derivation of n in terms of x, so that we can conclude that the given differential equation is an exact equation.
So that is how you prove the theorem 52, which states that if n, partial derivative of m in respect of y, and partial derivative of n in respect to x are continuous functions of x and y, then a necessary and sufficient condition that m dx plus n dy is equals to 0. B, an exact equation is that partial derivative of m in respect to y is equal to the partial derivative of n in respect to x. So for us to say that an equation is an exact equation, it should comply the condition that the partial derivative of m in respect to y is equivalent to the partial derivative of n in respect to x. So for us to solve or to find the general solution and for us to test for the exactness of an equation, we have here our steps. So for the first step, we have, first step, we have to determine the m dx and n dy. Next would be define the partial derivatives of m with respect to y, which is the m dy, and n with respect to x, which is the n dx. If the two derivation results with the same value, then the function is an exact equation. Next would be integrate the function f equals to m dx plus t of y is equals to 0, wherein t of y is your second term that has dy on it. So this t of y is a constant. So we will further explain this one. Fourth would be then derive the value of the integral of f equals to m dx plus t of y equals to 0 with respect to y. Fifth would be get the derivative value of it, then equate with the second term, which is the n dy. Sixth would be integrate the equation with respect to y. Seventh, lastly, would be substitute the integral value of t prime of y on the f equals to the integral of m dx plus t prime of y, so that we can have our general solution. Now, for us to more understand those steps, we have here our first example. Find the general solution of the equation 3x squared y cubed minus 5x raised to the power of 4 dx plus the quantity of y plus 3x cubed y squared dy. So first and foremost, first step would be determine mdx and ndy. So our mdx in our equation would be this one, 3x squared y cubed minus 5x raised to the power of 4 dx. Next would be the ndy, which is y plus 3x cubed y squared dy. So that would be our ndy. So the next one would be step 2. Find the partial derivatives of m with respect to y, which is the mdy, and n with respect to x, which is the ndx. So note would be, if the two derivation results with the same value, then the function is an exact equation. So in this step, we are going to test for the exactness of our equation. So for us to say that the two equation are exact equations. So first would be the partial derivative of m in respect to y, this one. So if we are going to derive that one, we will have the answer 9x squared y squared. Next would be the partial derivative of n in respect to x. So we have our answer here, which is 9x squared y squared. So since the two derivatives or the two derivation has the same value, so we can say that it is an exact equation. So now, for our third step, we have here, step 3, integrate the function f equals to m dx plus t of y equals to 0, where t of y is your second term that has dy on it. So, we have here the partial derivation of f all over, in respect with x is equals to m, x, and y. So, we know that our x and y, or mdx, is equivalent to 3x squared y cubed minus 5x raised to the power of 4. So, cross multiplying this one, we will have the partial derivation of f is equals to 3x squared y cubed minus 5x raised to the power of 4 dx. So, integrating these two, we now have f is equals to x cubed y cubed minus x raised to the power of 5 plus ty. So, why do you think that we have t of y here? So, it's just like we are adding a constant, or we are adding c, but it's just on t of y form. So, if I am going to differentiate f, this one, f is equals to x cubed y cubed minus x raised to the power of 5 plus t of y. If I'm going to differentiate it with respect to x, I will still have the answer of 3x squared y cubed minus 5x raised to the power of 4, since this t of y is treated as constant. Next would be the step 4. Step 4 is to derive the value of the integral of f equals to m dx plus t of y is equals to 0 with respect to y. So we are going to derive the answer on our step 3 in step 4. So if we derive this one, we have here d over dy, quantity of x cubed y cubed minus x raised to the power of 5 plus t of y. We will have the answer of 3x cubed y squared plus t prime of y. Next would be the step 5. Step 5 states that get the derivative value of it, then equate with the second term, which is the n dy. So we have here our derivative on this side, on the left side. We have here 3x cubed y squared plus t prime of y is equals to our n dy, which is our given, which is y plus 3x cubed y squared. So, using the addition property of equality, we will add up negative 3x cubed y squared both sides so that it could be 0 here and 0 here. So the answer would be that t prime of y is equals to y. So this is our step 5. So for the next step, which is the step 6, integrate the equation with respect to y. So we are going to integrate t prime of y equals to y dy. Integrating this one, we will have the answer of t of y equals to y squared over 2 plus c. Last step would be substitute the integral value of integral of t prime of y on the f equals to integral of m dx plus t prime of y. So we can use integral of m dx plus t prime of y equals to c. So since we already solved this one, the integral of m dx and the integral of t prime y is equals to c. So the integral of m dx is equals to x cubed y cubed minus x raised to the power of 5 plus our t prime of y, or the integral of our t prime of y, which is on the step 6, we can have y squared over 2 plus c, and our final answer would be the general solution, which would be the function of x cubed y cubed minus x raised to the power of 5 plus y squared over 2 equals to c. Okay, for the next example, we have here example 2. Find the general solution of the equation 2xy minus 3x squared dx plus x squared plus y dy equals to 0. So, we all know that our step 1 is to determine m dx and n dy. So, our m dx here would be this one on the left, this one equation on the left side, which is 2xy minus 3x squared. And our n dy here would be x squared plus y. So step 2, find the partial derivatives of m with respect to y, this one, and n with respect to x. So if the two derivation result with the same value, then the function is an exact equation. So the partial derivative of m in respect to y would be 2x. So we have here 2x. So next one would be the partial derivative of n. In respect to x, we have here 2x also. So since both derivatives, both results are the same or has the same value, then we can say that this equation is an exact equation. But our problem here is to find the general solution of the equation. Next step would be the step 3. Step 3 would be integrate the function f equals to m dx plus t of y equals to 0. So the partial derivative of x all over with respect to x is equals to mx and y. So we have here, we all know that our mx and y, or m dx, is equals to 2xy minus 3x squared. So we have here the partial derivative. So we are going to cross multiply it. So now we can now have our answer as partial derivative of f is equals to 2xy minus 3x squared dx. Integrating this 2, we can have now f is equals to, since it is in respect to dx or in respect to x, we can now have negative x cubed for this one plus yx squared plus ty. Next step would be step 4. Derive the value of the integral of f equals to m dx plus t of y equals to 0 with respect to y. So the answer of f on step 3 would be, we are going to derive it on step 4. So the derivation of the equation negative x cubed plus yx squared plus t of y in respect to y, or dy, the answer would be x squared plus t prime of y. Next, since we are going to use this answer on our step 5, we have here, get the derivative value of it, which is the x squared plus t prime of y. Then equate with the second term and dy. So our second term or our n dy is equivalent to x squared plus y. So using the addition property of equality, we are going to add negative x squared both sides so that we can get rid of x squared on the left side. So we now have t prime of y, since this is positive x squared on the right side and negative, add with negative x squared, it will be 0. So the answer would be t prime of y is equals to y only. Now, we have to integrate the equation with respect to y for our step 6. So integrating this equation, we can now have the integral of t prime of y is equals to the integral of y dy. Since we are going to integrate this one, we now have the answer of t of y is equals to y squared plus 2 over 2 plus c. So the answer would be t of y equals to y squared over 2 plus c. For the last step, we have here substitute the integral value of t prime of y on the f equals to m dx plus t prime of y. So we can use the integral of m dx plus t prime of y equals to c. So the answer should be the integral of m dx. So since we already have the answer of integral of m dx, would be since the answer of the integral of m dx is negative x cubed plus yx squared. Now we are going to add up the integral of t prime of y, which is y squared all over 2 plus c. So therefore our general solution would be negative x cubed plus yx squared plus y squared all over 2 plus c.
So for continuation, we have here example number 3. Find the general solution for the differential equations. We have here given a differential equations, the quantity of 8x plus 4y squared dx plus y times the quantity of 8x minus 6y dy is equals to 0. So based on the given differential equation, we can use exact equations on this one by determining if the partial derivation of each terms with respect to its opposite variable is equal or has the same value. So first and foremost, the first thing you need to do is to identify what is the value of our m dx and the value of our n dy. So m dx is equals to our first term since it holds the dx, and n dy is equals to the second term since it holds the dy. M dx is equals to 8x plus 4y squared, and n dy is equals to y times the quantity of 8x minus 6y, or can be written as 8xy minus 6y squared. So next step is to get the partial derivation of each in terms of its opposite variable. Getting the partial derivation of m in terms of y, and getting the partial derivation of n in terms of x. So first, let's get the partial derivation of our m. Partial derivation of m in terms of y is equals to the partial derivation of this equation in terms of y is equals to 8y. And next is the partial derivation of n in terms of x is equals to the partial derivation of this equation in terms of x is also equals to 8y. Since these two terms come up with the same value, then therefore we can use the general solution or general equation using the exact equation. So next, we integrate both sides by the value of our m dx. The integral of m dx is equals to the integral of the value of our m dx, which is the quantity of 8x plus 4y squared dx, is equals to partial derivation of these two terms is equals to 4x squared plus 4x y squared. So now we need to identify what is the value of our partial derivation of our function in terms of x and in terms of y. So in terms of x, it also has the same value of r n dx, and in terms of y, has also the same value of r n dy. So fourth step, the f of xy is equals to the integration of m dx plus t of y, which is equals to the 4x squared plus 4xy squared plus t of y. So in fourth step, we need to find the partial derivation of this function in terms of y. So the partial derivation of a function in the form of xy in terms of y is equals to the partial derivation of this equation, 4x squared plus 4xy squared plus t of y in terms of y. So we can now get the partial derivation of y in terms of y, 4x squared plus 4xy squared plus t prime of y is equals to the value of our partial derivation of a function in terms of y, which is the y times x 8x minus 6y, or 8xy minus 6y squared. So in finding the partial derivation of this equation in terms of y, results to 8xy plus t prime of y is equals to 8x minus 6y squared. And subtract both sides by 8xy, then we can get t prime of y is equals to negative 6y squared. So for our next step, to find the value of our t of y in this partial equation, we need to integrate both sides. So the integration of t prime of y is equals to the negative integration of 6y squared dy. So t of y is equals to t of y is equals to negative 6 integral of y squared dy. Then now t of y is equals to negative 6 times y cubed over 3, can be written also in negative 2y cubed. So for our last step, we just simply substitute the value of our ty on our partial equation, which is this one. So f of xy is equals to c. Therefore, the integral of m dx plus t of y is equals to c, which is equals to 4x squared plus 4xy plus negative 2y cubed is equals to c, or can be written as 4x squared plus 4xy minus 2y cubed is equals to c. Therefore, the general solution of our exact equation is equals to this form. 4x squared plus 4xy minus 2y cubed is equals to c. So next example, we have here example number 4. Find the general solution for the differential equation. We have here given differential equation. The quantity of 4xy minus 12x squared plus the quantity of 6y plus 2x squared plus 5 multiplied by dy over dx is equals to 0. So based on the given differential equation, we can rewrite this one into the form of m dx plus n dy is equals to 0. So we just simply multiply each terms by dx. So we can get the quantity of 4xy minus 12x squared dx plus 6y plus 2x squared plus 5 dy is equals to 0. So now we can now track what is the value of our m dx and the value of our n dy. So the value of our m dx is equals to 4xy minus 12x squared, and for n dy is equals to 6y plus 2x squared plus 5. Next step is to find the partial derivative of m in terms of y and n in terms of x. So the partial derivative of m in terms of y is equals to 4x, and the partial derivative of n in terms of x with this equation is equals to 4x also. Therefore, this differential equation is an exact equation. Therefore, we can use the general solution for our exact equation. So, for our next step is to find the integral of the terms that we used in this solution is the equation equals to m dx. So we need to find the integral of m dx. So therefore, the integral of 4xy minus 12x squared dx is equals to 2x squared y minus 4x cubed. Then next is to identify what is the value of our partial derivation of f in terms of x and partial derivation of f in terms of y. Then next, the f of xy is equals to the partial derivation at the integral of m dx plus t of y, which is equal to 2x squared y minus 4x cubed plus 2 of y. Then in this step, we need to find the partial derivative of the given equation in terms of y. So we have the partial derivation of this equation in terms of y plus t prime of y. So the partial integration of this derivation of this equation in terms of y plus t prime of y is equals to the partial derivation of f of our function in terms of x, in terms of y rather, which is equals to 6y plus 2x squared plus 5. So the partial derivation of this equation in terms of y is 2x squared minus the derivation of this equation in terms of y is 0, since the derivation of a constant is 0, plus t prime of y is equals to this equation, the value of our partial derivation of f in terms of y. So we have here 2x squared plus t prime of y is equals to 6y plus 2x squared plus 5. And we can now subtract both sides by negative 2x squared, which is equals now to t prime of y is equals to 6y plus 5. So now to find the value of our t of y, we just simply integrate both sides in this equation. So we have now the integration of t prime of y is equals to integration of quantity of 6y plus 5 dy is equals to t of y equals 6 integration of y dy plus 5 integration of dy, which is also equals to 3y squared plus 5y. So the value of our t of y is equals to 3y squared plus 5y. So we just simply substitute the value of our t of y on our partial equation, which is the 2x squared y minus 4x cubed plus t of y is equals to c, which is equals to 2x squared y minus 4x cubed plus 3y squared plus 5y is equals to c. Therefore, the general solution of our exact equation is equals to 2x squared y minus 4x cubed plus 3y squared plus 5y is equals to c. So that is now the answer on our example number 4, the differential equations. So for our last example, we have your example number 5, in finding the general solution of the given differential equation using the exact equation. So we have here e to the x times the quantity of x raised to the power of 4 y squared plus 4x cubed y squared plus 1 times dx plus the quantity of 2x raised to the power of 4 y times e to the x plus 2y dy is equals to 0. So we can rewrite this one into the form of m dx plus n dy is equals to 0, wherein we can simply distribute e to the x in each terms of the dx. So we have here the quantity of x raised to the power of 4 y squared e to the x plus 4x cubed y squared e to the x plus e to the x dx plus 2x raised to the power of 4 y e to the x plus 2y dy is equals to 0. So first step, finding the value of our m dx and m dy. So m dx is equals to x raised to the power of 4 y squared e to the x plus 4x cubed y squared e to the x plus e to the x. And for n dy is equals to 2x raised to the power of 4 y e to the x plus 2y. The next step, we need to find the partial derivation of each of these terms in terms of partial derivation of m in terms of y and n in terms of x. So we have now the value of, for the partial derivation of m in terms of y, then we now have 2x raised to the power of 4 y e to the x plus 8x cubed y e to the x. And for the partial derivation of n in terms of x, using those equivalent equation, we can get 2x raised to the power of 4 y e to the x plus 8x cubed y e to the x. So in this equation, we tend to use the value of our n dy for the integration part. So we have here the third step, integral of n dy is equals to the integral of the quantity of 2x raised to the power of 4 y e to the x plus 2y dy, which is equals to x to the 4 y squared e to the x plus y squared. So now we have here the value of our partial derivation of f in terms of x and in terms of y. The next step is to find the partial derivation of this given equation, and we just simply add t of x rather in the last part of the equation. So we have here the partial derivation of f of xy in terms of x is equals to the partial derivation of this given equation in terms of x plus the derivation of t of x, which is equals to t prime of x. Then next step is to get the partial derivation of this equation and equate this one in terms of partial derivation of f in terms of x, which is equals to this one, x raised to the power of 4 y squared e to the x plus 4x cubed y squared e to the x plus e to the x. So now the partial derivation of this one in terms of x is equals to x to the 4 y squared e to the x plus 4x cubed y squared e to the x plus 0 plus t prime of x is equals to the equivalent value of the partial derivation of our function in terms of x, which is equals to x raised to the power of 4 y squared e to the x plus 4x cubed y squared e to the x plus e to the x minus x raised to the power of 4 y squared e to the x plus 4x cubed y squared e to the x. Then we can now get t prime of x is equals to e to the x. So in getting the value of our t of x, we just simply integrate both sides. Then we can now get the integral of t prime of x is equals to the integral of e to the x dx, which is equals to e to the x. So the value of our t of x is equals to e to the x. Then next step is to simply substitute the value of our t of x in the partial equation, which is this one. So we can now get x raised to the power of 4 y squared e to the x plus y squared plus the value of our t of x, which is equal to e to the x is equals to c. Therefore, the general solution of our exact equation is equal to x raised to the power of 4 y squared e to the x plus y squared plus e to the x is equals to c. Therefore, this is the general solution of the given differential equation using the exact equation.
Okay, since we are done with those examples, let's try to answer this assessment. We have here 1, 2, 3, and 4. So the instruction would be test each of the following equations for exactness and solve the equation. Write your solutions and answers in a one whole sheet of yellow paper. Okay, for our example number 1, we have here the equation x plus y dx plus quantity of x minus y dy equals to 0. So first of all, the first thing we do is to determine our m dx and our n dy. So our m dx here is this one, and our n dy is this one. This is n and this is n. Our m dx is x plus y, and our n would be x minus y. Next step will be find the partial derivative. We have here partial derivative of m all over or in respect of y, and the partial derivative of n in respect to x. So we need to find their partial derivative so that we can test for exactness of the equation. So first, the partial derivative of m in respect to y would be now 1. How about the n dy? So our partial derivative of n in respect to x here would also be positive 1. Okay, for the third step, we have here integrate the function wherein c is equals to f equals to, f is equals to m dx plus t of y. So we are going to have our partial derivative of f in respect of x is equals to m dx, wherein we all know that our m dx is x plus y from this given. So m dx is x plus y. So using cross multiplication, we can now have the partial derivative of f is equals to x plus y dx. Now, we are going to integrate this too. So, integrating this one, we have integral of the, integral of the partial derivative of f is equals to the integral of x plus y dx. Now, we can now have an answer of f, wherein the integral of x plus y would be xy plus x squared all over 2 plus our constant, which is the t of y. So that would be for the third step. So for the fourth step, we have here, we are going to derive the answer of our third step. This one, we are going to derive this one. So deriving this one, we can now have d over dy, since it would be it would be in respect of y. So d over dy, quantity of xy plus x squared all over 2 plus t of y. Now deriving this one, we can now have an answer of x plus t prime of y. Next step, we have here the fifth step. Fifth step would be get the derivative value of it, then equate with the second term, which is the n dy. So this one, the answer, this one, x plus t prime of y, we should equate this one to our second term, which is the n dy, and our n dy would be x minus y. Then using the addition property of equality, adding negative x both sides, so that On this side, it should equate to 0. Now, we can now have x minus y minus x. So this one, positive x minus x would be 0. And this one would be positive x minus x, which is also equals to 0. So now our t prime of y would be equal to negative y. Now for our sixth step. So for the sixth step, which is our letter F, we have to integrate the equation with respect to y. We have to integrate the answer of our fifth step, which is t prime of y is equals to negative y. Integrating this one, we can now have an answer of, we have here, this one is integral of t prime of y. We will get rid of the negative. We can put here outside of the integral, we have here negative integral of y dy. So we can now integrate this one. Integrating, we will come up with the answer of t of y is equals to the negative y squared all over 2. This would be the answer now. Now, for our last step, we are going to substitute the integral value of t prime of y on the f equals to the integral of m dx plus t prime of y. Since we already have the answer of this, we have here the integral of m dx, which is this one, xy plus x squared all over 2. Then the integral of our t prime of y, which is minus y squared all over 2. So this one should also have plus c. This would be plus c equals to 0. So to use the form, we can now have our general equation xy plus x squared all over 2 minus y squared all over 2 equals to c. Therefore, our general equation is this one. This would be the general equation. Okay, for our second assessment, we have here the equation 6x plus y squared dx plus y, quantity of 2x minus 3y dy equals to 0. So, first of all, we have to find our m dx and our n dy. So, our m dx here is 6x plus y squared. And our n dy, we can have an equation of 2xy since we are going to distribute y in each term. We have here 2xy minus 3y squared. Now, next one would be the partial derivative. We have to find the partial derivative of both terms in respect to x and y. So, we have here the partial derivative of m in respect to y, and the partial derivative of n in respect of x. Now, we have here our partial derivative. So, for this one, in terms of y, we can now have 2y as our partial derivative, while this one, on n dy, we can also have 2y as our partial derivative. Since they are both, or they have the same value, this one, so we can say that this equation is an exact equation. So we can now find the general solution. For our third step, we have to integrate the function f equals to m dx plus t of y. Okay, since we have here our partial derivative of f all over partial derivative of x is equals to m x and y, or m dx, our m dx here would be 6x plus y squared. Okay, using cross multiplication, we can now have partial derivative of f is equals to 6x plus y squared dx. So, next step would be integrating this too. We have here the integral of the partial derivative of f and is equals to the integral of 6x plus y squared dx. So the partial derivative, the integration would be f is equals to, we have here y squared x plus 3x squared plus our constant, which is the t of y. So this would be the answer. On the fourth step naman, we will have the derivation. So we have to derive f equals to m dx plus t of y with respect to y. So we are going to integrate the answer of this. So we have here d over dy all over y squared x plus 3x squared plus t of y. Okay, so the derivative of this would be 2xy, this one, plus t prime of y, since it is in terms of y. Fifth would be get the derivative value of it. So we are going to find, we are going to use the answer for our fourth step. And we are going to equate this one to our n dy, which is equals to this one, 2xy minus 3y squared. So, using again the property, addition property of equality, we are going to add negative 2xy both sides so that we can get rid of 2xy here. So this one would only be t prime of y is equals to 2xy minus 3y squared minus 2xy. So we can now have t prime of y is equals to the negative 3y squared. We can now have this one. Next step would be integrating the equation with respect to y. So this one, we are going to integrate t prime of y is equals to negative 3y squared. This is dy. Next would be the answer. So integrating this one, we can now have we still have to get rid of the negative sign here. On this side, we can now have negative integral of 3y squared dy. So now we can now integrate this one. So we can have t of y is equals to the negative x cubed plus c. Okay, for our last step, we have here g. We have to substitute those values that we have solved so that we can have our general solution. So we have f, our general solution would be the integral of m dx plus t prime of y. So we have here, since we already solved our integral of m dx, we have here this one. So we have here y squared x plus 3x squared. How about our t prime of y? The integral of our t prime of y is here, which is negative x cubed plus c equals to 0. So, for us to have the final answer, we can get rid of c here, and using the symmetry, we can have y squared x plus 3x squared minus x cubed is equals to c. So, therefore, our general solution would be this one.
Now for our problem number 3, we have here given a differential equation. The quantity of y squared minus 2xy plus 6x dx minus the quantity of x squared minus 2xy plus 2 dy. So we need to show that this differential equation can be performed with the exact equation technique. Equation technique. So first and foremost, we need to find the value of our m dx and m dy. So the value of our m dx is this quantity, and for n dy is this quantity. So we have here y squared minus 2x y plus 6x for our m dx. And for our n dy, we have here negative quantity of x squared minus 2xy plus 2. So to know if this differential equation is an exact equation, we need to find the partial derivative of m dx with respect to y and n dy with respect to x. So the partial derivative of m with respect to y is equals to 2y minus the derivation of this one with respect to y is 2x, negative 2x. And for this one, partial derivative of n with respect to x, partial derivative of this one is 2x, so we have a negative 2x minus 2y. Or we can rewrite this one as negative 2x plus 2y, or 2y minus 2x. Since the partial derivation of m in terms of y and partial derivation of n in terms of x has the same value, therefore we can use the exact equation technique. So to start the technique of exact equation, we just simply choose one of these two to integrate. So in this juncture, I choose n dy. So the integration of n dy is equals to negative negative integration of x squared, quantity of x squared minus 2xy plus 2 dy. So is equals now to negative x squared y plus xy squared minus 2y, then plus t of x as an indication of this one m dx. So after that, we need to find the partial derivative of this function in terms now with x. So partial derivative of this function in terms of x, for this one, negative x squared y plus xy squared minus 2y plus t of x is equal to the first we need to find the partial derivative of f in terms of x and partial derivative of f in terms of y. So what is now the value of our partial derivative of f in terms of y? Is equals to m dx. So we have here y squared minus 2xy plus 6x. And this one is negative x squared plus 2xy plus 2. Yeah, that's it. So the value of our partial derivative of f in terms of x is y squared minus 2xy plus 6x. So now we need to derive this function in terms of x. Then we have negative 2xy plus y squared minus derivation of this one, negative 2y in terms of x is 0, plus t prime of x is equals to y squared minus 2xy plus 6x. Then subtract both sides by y squared and add both sides by 2xy. This would equal to 0, 0, 0. And left with t prime of x is equals to 6x dx. So since this is now our partial equation, we need to find the value of our t of x. So we have here given t prime of x equals to 6x dx. So to find the value of our t of x, we need to integrate both sides. So we have here the integration of t of x is equals to integration of 6x dx. That would be equal to t of x is equals to 6 integration of x dx is equals to 6 integration of x with respect to x is x squared over 2 plus c over 2. That would be written as 3x squared plus c. So since we have now the value of our t of x, then we just simply substitute the given value to our partial equation. So we have given negative x squared y plus xy squared minus 2y plus the value of our t of x, which is 3x squared, is equals to c. So this is now our general solution of the given differential equation using the exact equation. So for our next assessment activity, which is the differential equation number 4, we have given quantity of 2xy minus y dx plus quantity of x squared plus x dy is equals to 0. So we tend to use the exact equation technique for this one. But first and foremost, we need to know if the given differential equation is we are able to perform the exact equation technique. So to find that, we need to satisfy this condition. The partial derivative of m with respect to y must be equal to the partial derivative of n with respect to x. So first we need to find the value of our m dx and n dy. So the value of our m dx is 2xy minus y, and for our n dy is x squared plus x. So now we need to find its partial derivative with respect to its opposite variable. So the partial derivation of m with respect to y is equals to 2x, and the partial derivative of n with respect to x is equals to 2x also. Since these two partial derivative has the same value, therefore we can proceed to exact equation technique. So in this juncture, I tend to use the m dx for the integral. So the integral of m dx is equals to integral of quantity of 2xy minus y dx is equal to x squared y minus xy plus t of y as an indication of our n dy. So next step is to find the partial derivative of this function in terms of y. So we have partial derivative of f in terms of y, x squared y minus xy plus t of y is equal to the value of this equation. Here, partial derivative of our function with respect to x and partial derivative of our function in terms of y should be equal to 2x y minus y, and x squared plus x. So the value of our partial derivative of our function in terms of y is equals to x squared plus x. So now we need to derive this function in terms of y. So it is equals to x squared minus x plus t prime of y is equals to x squared plus x. Then we just simplify this equation. Then we have t prime of y is equals to x squared plus x minus x squared plus x is equal to t prime of y is equal to comes 0, then we have 2x dx. So this is now our partial equation, and we need to find the value of our t of y. So we have here given t prime of y is equal to 2x dx. So to find the value of our t of y, we just simply integrate both sides. So the integration of t prime of y is equals to the integration of 2x dx is equal to t of y is equals to 2 integration of x dx equal to 2 integration of x dx is x squared over 2 plus c, or can be written into the simplest form. This 2 would be equal to 1, then we left x squared plus c. So since we now have the value of our t of y, we just simply substitute this one into our partial equation. Then we have x squared y minus xy plus the value of our t of y, which is x squared. X squared is equals to c. So this is now our general solution of this given differential equation using the exact equation. And now for you to test your understanding about this topic, here are some sample differential equations for you to answer. Feel free to pause the video, guys. Thank you for watching and have a great day.